Hello.
Hello.
So I do have a difficulty. I don't know. I cannot access my account through my tablet. So probably I'm gonna teach over the PDF. I prefer to write myself, but today I could not connect to my account. I don't know what's going on. Okay, so let's see. Let's wait for a few minutes. So, and then I will explain a few things here. So, so 2 more minutes and see. The class is not going to be recorded. So I saw the slides is online. I posted a slide on Canvas, so you can look at the slides from yesterday. I'm not sure about Memorial Day. I should ask. I'm not sure. Probably it's going to be it's a holiday, so probably it's going to be off for all. Does anybody have any question about the slides yet from yesterday? Anybody has any question?
I think we get it.
What?
I think we understand.
So yeah, good. So okay, great. So let's see. I think we'll find 1 more minute and then we will start. Okay, so okay, so let's start. And then explain about notation, and then I will explain everything about what's going on. So let's see. Okay. Let's see if you can see my screen, and then we will start and talk about the symptotics. Can you see my screen?
Yes.
Okay. So yesterday I talked about when I say talking about algorithm, I say, oh, do we have an algorithm? It's really important that we take care of about the time, about the complexity of a storage, because we don't have memory all the time. So some of these things really important. So this is some of the notation we take about. But as I explained earlier, so when you run some of the program in your computers, and if I run it, maybe we got a different result. So, okay, it takes 2 minutes, and somebody said, oh, no, it takes 10 minutes based on the GPU, CPU, and and everything on the underlying. So that's the reason we ended up learning about the notation. Then you can compare to algorithm. For example, when I'm talking about the sorting algorithm, that sort number, there's so many algorithms, but when you want to compare them, you say, okay, I want to compare them, but should be a notation to define, for example, which one is better. So then that's the reason the asymptotic notation come in handy. We say algorithm performs Fn basic operation to accomplish tasks. So it means that my algorithm trying to do a function, which is calling the Fn, base n is the number of the task that's gonna do. Identify that function for asymptotic notation. Identify size of the problem. In the n is gonna be the size of the problem. It means that if the size is bigger, probably my algorithm takes more time, needs more storage. Count the number of operation in terms of n. Actually, this big notation, asymptotic notation, calculate the number of operation in terms of the number of the size of the problem that we have. So that's coming from that side. But things that, what does that mean? If I want to talk about, like, as I talk about time complexity, it means execution time. How long does it take for one algorithm to be done, to be finished? The problem is getting done. Time computer takes to execute that function. Operations like CFNN, for example, the time is going to be the number of the time that computer is going to take time. So there is a C, which is going to be a constant. So it's the overall, for example, if I say that sorting algorithm, like one of the sorting algorithm takes Fn, it means this Fn is like a function of the number of the tasks based on the, for example, if I want to sort 10 numbers, and if I want to sort 20 numbers, it's different because it's going to be f of 10 for 10 numbers, and if it's going to be f of 20 for 20 numbers. But as one of you guys asked yesterday, there is a constant, which is going to be the C. C is like a constant, it's considered to be depend on the speed of your computer. It means that if I sort it in my computer, maybe I have a really Core i9, and then I have really good memory and everything is faster than yours. But it doesn't matter because I say this sorting algorithm like merge sort takes, I don't know, and a square. Yeah, probably if you run it in your computer, it's faster than mine. So, but that C doesn't matter that much. Because it depends on the speed of your computer, varies from one computer to another. So probably most time we drop this constant as C because we don't care about it, about which computer. We are talking about overall which sorting algorithm is better. So let's talk about deployment of notation. If I have, let's see, for example, this is, let's example, this is like a one, I say, okay, I have an algorithm. The time, execution time for algorithm based on the number of the task, number of the input of that algorithm is considered with this function, n squared 4n plus 20. So think about, okay, if I have only one input, so it's going to be 25. And if I have two, it's going to be 4 plus 8, yes, 12, yeah, 32. So probably it's going to be changing based on the number of input. For example, I say, okay, sorting algorithm takes this time to execute. So as you can see, if I get this number n higher and higher, if I put it 100, 200, 300, this 20 is really a small compared to this number. It means we don't consider this constant anymore. Because if I have large number value, so I don't care about this constant number. So which says about asymptotic refers to a study of function as appears infinitely. It means that I don't care about if I have only 2, 5, or 6. I care about when I have so many number of the data sets. So here, as I consider this one, as I say, okay, this is the execution time takes for this function to be done. So I say, okay, n squared is dominant because 20 is, if n is become really big, this 20 doesn't have any value, this 4n doesn't have value too. So it's going to be dominant term because it's dominant to 4n plus 20, becomes insignificant as n goes larger. So at the end of the day, when I look at this algorithm, I say, okay, asymptotically, so the runtime is going to be n squared. I don't care about these values. Does it make sense?
Yes.
So it means that I try to just consider how long does it take for my algorithm to be done? Why it's important? So for example, if you write a code to just give like things that you have an app and you want to give a recommendation system to your user. So you want to recommend something. If I have 10 users, it's easy. I can write a code that is really, really slow, but because I have 10 users, it doesn't matter that much because at the end of the day, I can do it one by one. But when I have millions of users, the time and the number of people that's gonna do like, I want to do the suggestion to them, it matters. So that's the reason execution time is becoming important when you have a large number of the data. So that means that we consider the execution time based on the input that you have, based on the number of input that you have, and we consider that one based on gross. So okay, it's n squared. It means if I have 4 inputs, so it's going to be, if I have 2, it's going to be 4, for example, second. Eventually, the number of the data point is going to get higher and higher. So does it make sense? I will explain about big O notation. I just want to explain something about what is this mean. So what is this function coming from? Does anybody have any question up to now?
No.
So things that I give you, I have the function, which is going to be n plus 1. So if I have n plus 1, so if n is 1, 2, or 3, 1 is become important because it's become 1 plus 1 is become 2, 10 plus 1 is become 11. But if I have 1 million, is what that one number is become important? Like go back here, for example, things that this n is going to be millions. Is this 20 going to be really important when I compare it to millions?
No, right?
So yeah, you can drop it. It's like, okay, I don't care because at the end of the day, for example, like think you have, if you are a millionaire, 20 cents is not nothing compared to that million of dollars that you have. So you don't care about 20 cents. So that's like something like this. When it's become bigger and bigger, you don't care about the small numbers, which they don't change. So here, so we say, okay, drop insignificant term and constant because they don't care, because eventually at the end of the day, it's not, doesn't matter. Say function is like O(n) squared. So we say about big O notation, which I'm going to explain. But let's go here. I talk about some of these like time execution function, big O notations. Okay, if it's equal to 1, it means it's constant. It doesn't matter how many input I have, it's going to be constant. It's going to be 1. Doesn't matter. If I have million, it takes 1 second. If I have billions, it takes 1 second. Yeah, if I have 20, it takes 1 second. It means that the time execution is constant. It's not going to change. If I have my time execution to be log n power of 2, it means the growth is it's going to be log of 2. It means that you're going to, based on your input, you're going to get log of that. So it's going to be better. It's not that like constant, but it's good. It's not bad because it's going to be a small again. And then I have a linear, Gaussian linear. It means that if I have 2 input, the output is going to get 2, for example, second. If I have 10, it's going to be 10. It's going to be gross linearly. And then I have growth is going to be n log n, which is going to be faster than linear. Growth is faster. It means the number is going to go higher, but it's still better than n squared, which is the quadratic. And then we have 2n squared. It's going to be exponential. It means if the number of the data is small, it's okay. But if it's become really huge, it takes a long time. All of these things I explained because it's important. At the end of the day, if the number of data is become higher and higher, you care about this like execution time. Does anybody have any question up to now? Okay, good. So let's go back to, let's look at this one. I have a table here. That's the reason I want to explain. Let's talk about, okay, I have an algorithm, like things that we are doing is sorting algorithm. I'm going to sort numbers. For example, if I have number 20, 30, 12 zeros. So you're going to sort them from smallest to biggest numbers. So let's think I have this number. It means that, and I have 4 different algorithms. And this function shows the execution time for any of these algorithms. I say, okay, I have only one numbers. I'm going to sort that numbers. If I sort these numbers, if this is the execution time for the first algorithm, it means it's going to be, for example, 0 seconds, doesn't take that much time. For the second one, 2. For n squared, it means it takes 1 second. And if it go to 2 power of n, it's going to be 2 seconds. But let's see. Okay, so okay, that's not bad because I have one input. Let's do 2 inputs. So it means that the first algorithm take 1 second, the second algorithm take 2 seconds, the third algorithm take 4 seconds, and the last algorithm take 4. It's still okay. I don't say, okay, taking 4 seconds is not bad to just do one sorting algorithm. I increase this one. I say, okay, the number of the input is going to be 4. The first algorithm takes 2 seconds. The second algorithm takes 8 seconds. The third one 16, and the fourth one is 16. It still is not bad. So because it's 16 seconds is not bad. But let's see, if I have 8 numbers and I want to just like sort them, the first algorithm takes 3 seconds, the second 24, the third 64, and look at the last one actually, 256 seconds. You can see just changing from 1 to 8, you can see how much it changed. It's really exponentially changed. Then I have 16 numbers. The first algorithm takes 4 seconds. It's not bad. And the second and third. And look at the last algorithm. So it takes 65,000 seconds to finish that one for like just sorting that 16 numbers. And if it go to 32, look at this, how it's exploded. You can see I just have only 32 numbers I want to sort. You can see how is the difference. The first algorithm is really, really good because it doesn't matter when I go from 1 to 32, it doesn't take that much time. The third algorithm is bad. It's not good, it's bad. But look at the last algorithm. It's explode. It means that if I have millions of numbers I'm gonna sort, it takes forever. So probably it's not gonna be done in a day or 2 or 3 or something like that. Does it make sense?
Yeah, that makes sense.
So does anybody have any question? Does it make sense why it's important? Why now we care about like this execution time, which we define like this function that we define and we call it like asymptotic notation? Does it make sense for everyone? I'm just talking about the importance of why it's important. And that's why I care about these things. Okay, sounds good. Yeah. Now, it's become really important. That's the reason. So when you are going to get a job, they ask you about like this asymptotic notation to make sure, because if you want to run a code, write a code for the company, and it takes, I don't know, 10 days to be finished, it's nobody going to want it. So I care about, because if I have like social media and I want to make it a suggestion or do something, if the number of users get high and the algorithm takes, I don't know, these numbers to be finished, that the algorithm is like garbage. So it doesn't make sense. It doesn't work. So because it doesn't give the value to it. So that's one of the things. So you need to make sure based on the number of input, what is the algorithm going to generate and what is the algorithm going to be? Does it make sense?
Yeah.
Okay. So let's go and see here. Okay, this is really important. This graph shows you how important is it. So this is the common grouse function, grows as n grows. Look at here, I have these plots. This is the n, this is the black one, this n, you don't see that it's here. So you can see this one. For example, it means that if the number of the input is small, so probably this is the number of input, probably it's not going to be that bad. So you're just going to be constant or just log of n, or it's going to be n log n. But as you can see, when the numbers get higher and higher, you can see how explode, how long does it take to finish. You can see, for example, for 2 power of n, you can see how it's exploded. It means after 4, it's going to be really, really bad. So it's not going to be good. So that was one of the most important things you need to learn. So that was the first things I just want to explain, just because I want you guys to know about why asymptotic stability is important. I'm going to go and teach why, about how you calculate it, how do you get to this function. But first of all, you need to know why it's important, why we care about it, and how you calculate that one. I will explain that one in just a minute. So is it clear for everyone?
Yes.
Yeah, I think it's clear.
If I ask you guys, okay, I have please write me okay, I have an algorithm. So let's see, let me ask you guys. So let me write it in chat. Actually, I'm so sorry, I could not type in my tablet, so it's hard to chat right here. Let's see. I write it in the chat, so probably I can do something, but just give me one moment. Maybe I can annotate like here. So let me open another chat here, another function. Okay. Okay, let me write it here. Let me share my screen and just write it here, and then we can talk about it. Then can you see my screen? Okay.
Yeah.
Yes.
Let me annotate here. I have this ns squared n power 3 plus like ns squared plus 1. If I ask you guys, so okay, I said, okay, I wrote an algorithm. This is the n is the number of input that I'm gonna give to my algorithm. So what is the asymptotic notation for this one? So how do you say? Is it gonna be what? If I'm gonna consider f?
The big O of n cubed.
Yes, exactly. Why?
Because we keep the
Because n
highest
cubed
term.
is the largest function.
Yes, because at the end of the day, one is really important. No, because ns squared, n is become, most of the time when you talk about asymptotic notation, you don't care about the small numbers. You're talking about really huge and big numbers. So probably that number 1 is nothing. And if I compare n cube and ns squared is nothing compared to n cube, when n is become higher. Am I right? So this is gonna be this one. Does it make sense to everyone? Yeah. Okay, so let's go back here. So let me remove the annotation. Okay, and let me close my annotation and talk about here. Okay, so let's go back and talk about what is asymptotic notation again and how you calculate them. Okay, I know that is important. I got it. So, but how can I calculate them? So I know that you write, okay, I talk about n squared, but where are they coming from? So we say asymptotic complexity, which is really important, is runtime of an algorithm as a function of input size n for large n. So another type I want to consider, so it's the runtime when the algorithm is going to be done, it's going to be finished based on the input size, but not for a small n. It's going to be for large n. So we are going to express using only the highest order terms, as I explained. We talk about like n cube other than n square, the expression for the exact runtime. So for example, I come and say, okay, I wrote an algorithm, takes 200 milliseconds. Is it make sense? Does it have any value for you? If I say, I wrote an algorithm that takes only 300 seconds. What is the issue with that? If I come and tell that.
You say an algorithm taking 300 seconds?
Yes.
Because it might be different depending what system you use with
Yeah.
the algorithm.
Yeah, probably, because maybe you will, first of all, you will ask me, okay, which kind of like computers did you use? What is the memory? What is like what is the the specification of your computers? That's one of the most important things. If you report something in second numbers, you need to provide the specification of your computers first. So I say, I run this code in this kind of specification of this computer, it takes 200 seconds. So, but as I explained earlier, instead of exact runtime, we say like tera notation or big O notation. This is what does it mean? It means to describe behavior of function in limits when n goes to infinity. So we are writing using asymptotic notation. That's the reason asymptotic notation has become really, really important. Is it clear up to now?
Yes.
Yeah, another things, yes. One of the good things that one of you guys mentioned, so it means I want to write an algorithm to make, if I don't know the exact number of the input right now, I can predict, because if I know it's going to be n squared, it means based on if the numbers get higher and higher, it takes more time. So you're not going to talk about a specific number because you don't know how big the input's going to be. Okay, let's talk about some of these notation. So there are different notation we talk about, like big theta, O, omega, small o, and small omega. So we are talking about different function. This is different asymptotic notation. Any of these notation have meaning, and then we talk about them and say, well, why we think this is important and the other things. So, but we have 5 different notation actually. So this definition function over the natural numbers. For example, we say, oh, f of n, this is the function of n. It's like a big theta of n squared. It means that describe how fn grows in comparison to n squared. It means gonna be how it's working. So we want to have a set of function in practice used to compare 2 function size. For example, I say, okay, this is my first function, this is my second function. What is the difference? Which one is better? The notation describes different rate of growth that we have between functions and set of the function to based on the inputs and then what's going to happen as a greater rate of growth when you have it. So let's talk about this one. This is the first important things that we are going to talk about first. This is going to be theta notation. So what is going to be for function g of n, things that I have a function. When I go back here and like say, okay, this like algorithm is a theta of n squared. What does that mean really? So what does that mean? What is going to give me? I say, okay, when I'm talking about the function g of n is going to be n squared and cube anything. We define theta of g of n, big theta of n, as this set. We said theta of g of n is all the function which exists a positive constant C1 and C2, and then there is so we have n and 0. So we saw such that from that point onward, we have like fn is gonna be between C1 Gn and C2 Gn. What does that mean? Look at this function. This is my function f of n. It means from this point onwards, after that, this function is gonna be between this like C1 of the g of n and C1 Gn and C2 Gn. It means it's gonna be inside this bound after this point. It means that set of all functions that have the same rates of growth as g of n. What does that mean? So it means that if the g is gonna be growth based on f, for example, if n is based of this n, this g gonna work like this. F of n is gonna be all the function that's gonna have exact same rate of growth. So we say Gn is an asymptotic tight bound for Fn because it's going to tie the bound for Fn. Does it make sense? Probably something new that you never see in the past. So probably it takes time to just.
I think I understand.
Okay, you got it? Yeah. We're trying to say, okay, find a bound for this function. Say, okay, all the other functions that have the same rate of growth between these. It means when we say, okay, theta of n squared, it means that the function has like gonna work like between set of all functions have same rate of n squared. It means when n is become larger and larger, it's gonna be explode with n squared. So let's see. For function g of n, we define theta g of n, big theta, we define it like this. So technically, if I want to say this one, I'm going to say, because you can see here, I define it, if I go back, so I define theta of g of n, be all the function, whereas that function is going to be between these bounds. This is not going to be equal. Actually, it's going to be all this set. Am I right? This is going to be all this set. It means that f of n, it belongs to this set, this yellow set, because it's going to be inside that yellow set. Instead of technically f of n is going to be in like the inside of this bound, we use f of n is equal to theta g of n. It doesn't mean it's equal. It means it's going to be inside that bound. So, but we accept it either way. We say, okay, theta f of n is going to be like a subset of the theta g of n, or you can say that it's going to be equal. And then what's going to happen? It means that f of n and g of n are non-negative for large n, because as you can see here, they're non-negative. It's going to be equal to 0, or it's going to be higher than 0. Both of them, f of n and g of n, are not going to be non-negative for large n. Does it make sense?
Yeah, it makes sense.
Yeah, because we need this one, we gotta go and explore these things, and then it's gonna be part of your quiz for like Thursday. I just want to make sure you guys understand what's going on, what does that mean. So probably just if you have any question, let me know. So let's see an example. So let's go back. Let me just annotate everything here. So probably it's gonna be easier. Oh, let's go back. Okay, so okay. I have these things. I say, okay, find all of the function, positive constant, and then a not so such that after that, this is going to be bound between these two. Okay, let's see this one, for example. That's the reason why this is definition is becoming important. It means that instead of telling that 10n squared minus 3n, I want to find the set of function. It's going to be big theta of n squared, as you can see. It means it's going to be bound between n squared, these numbers. It means the growth of this function is going to be as same as growth of n squared. That's the reason you remember I said, okay, we can get rid of 3n because n squared, you can just ignore this one. But this is coming from the definition of the big theta of n squared. Does it make sense?
Yeah, of course.
That sounds good.
Okay, so let's go back. Okay, it doesn't go to next page. What happened? So probably there is something else. Okay, let's see. Okay, now I know this is this is some part of the homework you are gonna have. I'm gonna give this one to you, as I'm gonna say, okay, I know that 10 n squared minus 3n is gonna be big theta of n squared, but how you find this? Because if you want to prove this one, you should find this one. You should find the C1, C2, and N naught. So, and then show this one is going to be considered. It's going to be work. You should show this is going to work. So, we should, what constant for N naught, C1 and C2 will work. It means if I have this function, what's going to be the numbers? Can anybody find that numbers for me? Just any idea how you find the C1, C2, and N naught?
Couldn't you just choose like a really small C and a really big C2?
No, actually, maybe because we cannot consider any C, you know, you need to find this relationship actually, and you need to find n naught. So it means you need to find the exact numbers. Anybody has any idea how you consider that one? How you can consider n naught, how you find C1 and C2?
Never mind.
I'm so sorry, your voice is
No,
coming.
it's fine.
Anybody has any idea? So let's, any example how it
So
works?
someone said just to substitute the equation into the inequality first.
So you mean this one?
Yeah.
So, okay, let's see. Just, okay, what do you want to do? So just put 10 ns, sorry, okay, I'm trying to, ns squared minus 3n. Okay. And then find this one, C2 ns squared. Okay. So what's going to happen? So if I'm gonna move this one, for example, it's gonna be C2 minus 10. Does it make sense? So it's gonna be C2 minus ns squared. I just bring everything onto another side, as you can see. Just bring 10 to this side, it becomes C2 minus, and it's gonna be plus 3n greater than 0. Does it make sense? I say, okay, I can just get n out of these things, and it's going to be positive. So because we know it's going to be positive, so C2 minus 10 n plus 3 is going to be higher than 0. Okay. So this is going to be the multiple, all of them here. So what I'm going to say, if I know this is going to be positive, if I know n is positive, what does that mean? This is some multiplication of two numbers. If one of them is positive and we have all the equation to be positive, what's going to be this one? So yeah, this is going to be positive too, because this is the multiplication of two positive numbers positive. So it's going to be, for example, so we should consider C2 minus 10 n plus 3 is going to be positive. And then you see, okay, if n is more than 1, so because it's going to be positive numbers, so you can consider and find C2 based on this equation. Does it make sense?
I'm a little confused on the math, but I think I could do it by myself. I'm a little confused on the handwriting, I'll be honest.
Oh, I'm so sorry. Just I will make sure tomorrow I can contact the university to get access to my tablet, can get access to Canvas on the other thing, so I can write it.
No, it's okay. I understand. I'm just saying.
Yeah, so you need to write this one down. So this is equation, and those both sides, and move them and just find this thing. And you need to find, based on that, you need to find the n, which n is gonna be that one. So let's see. Let's remove this one. So and let's keep going.
Are the n natural numbers?
Yes. Yes, n. Yes, it's natural. As I explained here, let me go back. So let's.
Oh no, I remember. I was just saying.
Yeah, it's not. Yes. Yeah, so it's going to be natural numbers. So let's go back. Okay, so let's see. We are going to find this one. Say, okay, make C1 a little smaller than leading coefficient and C2 a little bigger. We can consider that one too. And to compare order of growth, look at the leading term. For example, find these values, consider that one, and then you will find this one. Then what we are going to do, exercise, we want to prove that ns squared over 2 minus 3n is going to be this one too. It means what? How do you prove it? If I give you that, prove this one, how do you prove it? For proving this one, that this function is the big theta of n squared, you need to show this one. It means you need to calculate C1, C2, and n naught. If you find any C1, C2, and n naught that just shows this equation is going to be working, so you are done. You just proved it already. Does it make sense?
Yes.
It means if you could not find C1, C2, or n naught, it means they are not a big, like the theta notation. So that's one of the things. Most of the homeworks that you're going to have for the first one, for example, I'm going to give these ones to you and say, prove this one is going to be theta of n squared. Or is it true? Is this sentence, is this equation true or not? For example, one of the questions for the quiz can be this one. I write this one, I say, okay, prove it, or I say, okay, is it going to be true or not? That's one of the things you need to calculate. This part of the class is more math. You need to calculate it. Like, as I explained earlier, you need to handwriting, write it, how to calculate it. And then after that, we are going to go to pseudocode, coding part. But first of all, we need to make sure you got this one. Does it make sense up to now? Okay. Hopefully you got it. So. Okay, I'm going to ask you a question. Is 3n cube is going to be like inside subset of the theta of n power of 4? Is it true?
Wait, so what does the E looking symbol mean again?
This one means
Yeah.
subset. It's the exact same thing. It's a big notation. As I explained earlier, if I go back, I said there is 2 ways you can see. Because this f of n is going to be between this one. Instead, this is subset. It's like the same. It's like is equal to big theta of notation. We can use both of them. They all have the same meaning. This is the explanation too. It means that is equal or subset is going to be the same. It means that you need to find C1, C2, and n naught for just calculate. Do you think this is going to be true? Do you think you can find any equation C1, C2, and n naught for any of these 2 examples? So let's give, I don't know, 5 minutes. I'm gonna give you guys 5 minutes to just, let's see. Anybody can tell me just, is it true or not? The first one and the second one. Just you have, just start writing like in the paper to see if you can find the C1 and C2. Just play with that. Just you have 5 minutes and just we will get back and then talk about it. Anybody has any idea? Just think about it and just I will get back to talk about that. We have 34 students only. I see 3 response. Any other people? So let me give you some hints. Let's go back to the plot. if I want to talk about Fn, it means that this Fn, the growth rate is going to be similar to this G of n. It means the growth rate of n cube should be similar to, is going to be between n to the power of 4. Is this possible? Any other student? Don't be shy. It doesn't matter if you say it correct or not. So at the end of the day, we don't care about. We're trying to talk about it and learn about how it works. Okay, let's make it easier. Let's explain something. I want to make it really easy. So let's go back here. I want to have some example for you guys. Maybe it makes it easier to understand. Thinks that this n power of 4 is the like a speed of running of a rabbit, and n cube is gonna be like a turtle. So is it gonna be the same? It means I said, let's go back. I want to make it like really easy to understand. Probably is easier. Things that C1GN and C2GN, let's consider GN is going to be a specific like kind of rabbits. So this C1 and C2, it means there are two different rabbits, but they're going to be a specific same rabbit. It means they just run in a specific speed. They're going to have same specific speed. And then I have like a turtle in the middle. So do you think it's going to be possible? And I can say that if I have a turtle and I have two rabbits, are they going to run in the same pace? It means the turtle is going to run between two rabbits. Is it possible? If they're running, if it's n high, it means they're running in a higher speed. For sure, no, because at the end of the day, two rabbits are going to be faster than the turtle. So probably it doesn't matter how fast the turtle is going to run. It's not going to be between the two rabbits in running. So does it make sense? It means this speed is not going to be the same. So that's the thing. The first response to the first question is not. Because for large n, it means that it's going to run faster. It's not going to be in the middle of that. Does it make sense?
Yeah, that makes sense.
Oh yeah, that makes sense now. Yeah.
Yeah, I think I just trying to explain it some way, so probably is easier to understand. It means that you need to find that connection. So, okay, so let's see. I think this is, how about the second one? Probably you can think about the second one. Let's.
I think. Oh, sorry. I thought you were asking. I think for the same reason, it's also no.
So let's do something. We should prove this one. Let's give you one day. So tomorrow, before the class, we are going to talk about this one. Let's just prove it. I explained something, but just try this one and see if it's going to work or not. So just try the second one. Write it like I will post the presentation, but make sure before the class, what I'm going to do, maybe I will add a quiz like this, show that this is going to work or not. So we'll be ready. Just check this one out. So tomorrow, so see if it's going to work. Is there any C1, C2 or a not you can find to prove is it correct or not? Does it make sense? When I was talking about how do we prove it in paper, it means you need to see, for example, if I write this equation, it means I put 3n cube between C1 and n power of 4, C2 and power of 4. And I will show this one. It's like, okay, it's going to be 3n square and n cube less than equal to C2 and like a power of 4, and then I will divide everything by n third, and then I will find if n is gonna be greater or not. Let's do that one. Let's write it. Hopefully, I know I'm so sorry. I'm trying to write the best annotation, but let's see if I can type it here. So let's see. You say okay, 3n power of 3. Can you see it?
Yeah, we can see it.
Okay, it's gonna be, okay, where is it? It's gonna be less than equal than C2 n power of 4. Okay, let's go down. So you understand what's going on here, am I right? So let's do something. I say n is not natural, so it's going to be positive. Let's divide everything by n squared. So this is going to be n, 3n is going to be less than equal to C2 ns. Let's divide by n cube actually. It's going to be 3 less than equal to C2 n. Does it make sense? Then I will, what I'm going to say is, okay, I found C true, it should be greater than or equal 3 over n. This is going to be the first thing. So this is the first equation I found. This is going to be C2. It means C2 is going to be greater than these values. And then you need to find C1 and find the n and see if it's going to work or not. Probably if you start looking at this part, you will see it's not going to work based on this explanation because of the n. So you will find the number is not going to work. So the equation is going to be some way it's not going to work. But this is the way that you calculate them on papers. So if you want to prove it's work, you show it's proving it's going to work. So I just want to say, I'm not going to write it here, but this is the way that you calculate if you can find any C2 to do it or not. So, okay, we just got the first part. Just never forget. So it means that you need to find the rate, like the pace between these two paces. Probably if you remember the rabbit example, probably you will not forget it. So. Yeah, good idea about the second one, but just prove it and then we can talk about it tomorrow, actually. I will explain everything. I want you guys, all of you guys, try to work on the second part to see how it works. It's not something really complicated. This is the example. You need to find C1, C2, and n naught. So that's it. It's just going to be really easy. Just calculate that one. It's like a really inequality math. So you can calculate that one. What I'm going to post, I'm going to post one page of note, which is going to show some of this basic about inequalities, like if you have the floor, ceiling, and everything, because you need it in this class actually for this kind of homework. So I will post one note, let's just remember, let's just bring some memory of about the math part. Okay, now I know about big theta notation. So that was the one that is, it means that what is the big, look, what is the growth of that algorithm. Let's go and say, okay, I talk about big theta. One of the most important asymptotic notation is going to be big O of n. Everybody talk about big O of n, but what is the big O of n means? So for function like g of n, we define big O of g of n to be set of this one. It's okay. Big O of g of n is all the fn when you can find a positive constant c and n naught from that n naught, that f of n is going to be greater than 0, but it's going to be less than cg of n. Let's see. For example, what does that mean? It means my function is going to be less than this function after n naught. It means that probably after a while, the growth of cg of n is going to be more than f of n for sure. So it's going to be happen. So it's going to be set of all function whose rate of growth is the same as or lower than of g of n. So it means it's going to be the same because we are going to have the lower bound because it's equal. It's going to be the same or lower than that one. So that's the thing. G of n is an asymptotic upper bound for f of n. As you can see, G of n is the upper bound. It's going to be, as you can see here, f of n is going to be upper bound of the like. So the way that we define, we say, something is really important. If I know f of n is big theta of g of n, I can say f of n is a big O of g of n too. Does anybody know why?
Can you repeat that, please?
Why?
Could you repeat that, please?
So, okay, let's see. I know that I told you guys that f of n, my function is big theta of g of n. If I know that, I can tell that f of n is big O notation of g of n2. It means this is going to be the one-way equation. It means if I know that my f of n is a big theta notation of g of n, for sure it's going to be O of g of n2. Do you know why?
Since big O of n still has the same upper bounds.
Yes,
If,
exactly.
yeah.
If you go back here, let's go back. You can see here. As you can see here, when you have a theta of g of n, it means f of n is equal or lower bound up. G of n is going to be upper bound for f of n, for sure. It's going to be, you can see there is an upper bound c to g of n is going to be upper bound. What does that mean? Because look at this example, this explanation. If I keep c of 2, but put c of 1 equal to 0, this equation is become 0. F of n is bigger than 0, is less than c to g of n. It means just considering c1 to be 0, I'm going to go back to big O of O notation. So you can see here, just what I did, I put c2 equal to c and just c1 equal to 0. As you can see, it means that if I have theta of g of n, I have O of g of n2, because just I change c1 to be 0, c to be c. So that's the definition. It means theta of g of n is a subset of O of g of n. Why? Because as you can see here, look at this plot. The other plot was like between, was like a sandwich in between. It means that this one is have this theta of g of n is going to be subset. But this way is one way. It means if I know my function is big O notation of g of n, it doesn't mean it's going to be big theta of g of n too. Look at here, y, for example, because I could not, I know I have a c2 here. I could not find c1 that it's been sandwiched in the middle of the both of them. This way is one way all the time. So does it make sense?
Yeah, makes sense.
Yeah. So that's the most important thing. Anytime I give you any question, I ask, okay, is it a big O of n or not? What do you need to do? You need to write this function, find this C1 and n naught. If you could find it, it means it's done. You calculate it, you just show it. And if I know that I tell you, okay, this function is theta of g of n, you can say, oh, this is big of O of g of n too. That's one of the most important things, you know. Okay. So let's go to an example. We have a big O of g of n. So it's f of n. There was a positive, there exists a positive number, c and n naught. The way that, for any n greater than n naught, we have f of n between 0 and less than c g of n. So let's do this one. Any linear function, in a linear function is going to be a n plus b is in O of n, is big O of n squared. Does anybody know why?
Because since it's linear, it's underneath the bounds of n squared.
Yes, exactly. Because it doesn't matter what you have for a and b. The growth on an plus b is linear. And then the things that you plot this one, let me plot it, for example. Where is the annotation? Okay, let's do this one. Things that this is n squared, for example. Actually, we don't need the negative part because we talk about n positive, so n to be natural. So probably I need only this part. So I have this part. Oh, what happened? Let's see. It doesn't work. Okay, we do have this one. So this is gonna be n squared, for example. And linear function doesn't matter for a of b, it's going to be like this. It's going to grow linear. And this is going to be, every time it's going to be lower bounded. This is going to be upper bound for this. So every time, so as you can say, this is an plus b is going to be big of n squared. Does it make sense?
Yeah, that makes sense.
Okay. Now let's the other thing. Let's, for example, it shows that 3n cubed is equal to big O notation of n4, n power of 4. So you need to find C and n naught. So how you find these two until it's found, it shows that it's going to be possible. Does it make sense?
Yes.
Okay, so that's the other things you need to calculate. So it's okay, this is the way that I'm going to calculate. This is the calculation. That's it. So I think that's probably clear, but you need to show this one. You need to find this equation is going to work. How does it sound? Is it clear or? If it's clear, let's go to the next. Let's close this annotation and then. Okay, before going to big omega, I want to give you 5 minutes and then I will show another example. Just before moving all of this one, just example, what is C and n naught and everything. Just give you 5 minutes break so I can go back and explain some of this example with writing. So does it sound good?
Yeah, so we're taking a break right now.
Yeah, 5 minutes break. Mhm.
Cool.
No, there is no presentation as part of the grade. I will update the syllabus actually. We have final exam. So let's go, and I think we have 5 minutes done, so probably 1 more minute. So let me share my screen to show one of the examples. Can you see my screen?
Yeah, we can see it.
So I'm gonna post this one when we finish about big O notation. I'm gonna post this note. As you can see, this note explains everything in details. So about how it works, for example, this is the explanation of big O notation again. It's the exact same thing that I have in the PowerPoint. So does it have some explanation about how it works, just in details? As you can see here, we have the Fn and C of Gn. Let's go here. I want to talk about this one. So we say, okay, I have 10n plus 100 is big, it means big O notation of n squared minus 10n plus 500. How they do that, for example, what they did, if you, for example, look at, see, I just plot this like 10n plus 100. I plot the first line, and what I did, I plot the second one. I want to show that this is the big O notation. I plot both of them and see, I show that from some point onwards, everything, this is going to be big, is going to be upper bound. How did I find it? I just come here and calculate and everything. And I realized that because this is going to be C, because you need to find upper bound, it's going to say, okay, for Z after and not, so it's going to be between this one and C. I say, okay, consider C equal to be 1. So it means after that, and I found these numbers. It means after 40, so it's probably plot bad. So it's going to be here. After 40, you can see this is going to be higher. The value is going to be higher. So you say, okay, I consider n not equal to be 40 and C equal to 1. So this equation is going to be considered. So it's going to be true. Does it make sense? Probably one of the way to just prove this one, you can plot them and say, okay, based on consider C1 and then based on consider n not going to be this value. So I show it's going to probably work and it's done. Does it make sense?
Yeah, that makes sense.
Okay. So, and then let's see. I want to have another example of like about theta notation. So let's see, for example, this is going to be, for example, one of the homeworks, probably, or any other examples, okay, or final exams. So your midterm, prove that like a square root of n plus 10 is equal to big theta notation of the square root of the n. So how does it work? So I say, okay, if I want to prove this one, it doesn't say it's correct or not. It says prove it. For if I ask you to prove it, it means you should find C1, C2, and not, because this is going to be the theta, big theta notation. For big theta notation, you should find C1, C2, and then not. If I found that one, it's done. Everything is done. You don't need to be worried about this thing. That's the proof. So I say, okay, there are different possibilities for considering C1 and C2 and not. It doesn't mean that I just need to have 10. For example, here as I can choose C to be 2, and this plot is going to be totally different, and not is going to be different too. One of the way to solve this one, it means, so I could just consider, I want to say, okay, I consider C1 equal to 1, C2 equal to a square root of 2, and not is equal to 10. I want to prove this one. I want to show this is going to be true. Based on this number considered. How can I prove it? Because I need to come to this point. There is a way. I say, okay, I consider n not to be 10 One of the definitions say that n should be greater than equal to n naught. So what's going to happen is going to be n equal and greater to be 10. This is one of the things. So, but as you can see here, I need to generate this, C, like this part, f of n less than C2gn. It means that I need to have f of n and I need to generate C of n, one equation. So what is the f of n? F of n, it means it's n plus 10. It means I need it. So if this is the equation, like this one, how can I reach to this point? One of the clever ways, okay, this n is like, because this is number 1. Instead of writing number 1, I can say 2 minus 1. 2 minus 1, if I consider, what I'm going to do, I say, okay, this is 2 minus 1. What I'm going to do, I say, okay, let's consider this part. This is going to be C2 squared. And then minus, not a square, like a square, like, and then minus 1n. So this is going to be like, this is going to be the definition. So, okay, what's going to happen if I do this one, if I consider C2 squared to be equal to 2, what's going to happen? So I do have this definition. So I can, because this is minus n, I can bring n to the other side. So I can have n plus 10 less than equal C2 squared n. So I got this part actually, because now I have f of n less than equal to C g of n. Because after this part, what I'm going to do, I have this part actually. So I write, okay, the n plus 10 less than equal C2 squared n. And then I get the square root. So you can see here, this is going to be happen. This is the first part. I just proved the first one. It means I just need to consider C2 squared to be equal to 2. That's it. I found C2 right away. Does it make sense? Anybody has any question?
So for this example, are you working backwards?
Yes, actually, yeah, I consider n naught, but finding with n naught, I found C1 and C2. The only things I consider are just n naught, because this is the things I did. I said, okay, I know that n equal greater than 10. How can I reach out to this point? I realized I need 10. I said, okay, I need minus n because I need to bring n to the other side. So what I do is I say, okay, consider 2 minus 1 is going to be that one, and consider this 2 to be C2. Yeah, I just reverse engineering, but based on the n naught equal to be 10. That's the only things I know. And then based on it, I found what is C2. This is the first part. I found the upper part, but I need to do lower too. What I'm going to do for the next part, I say, okay, I know minus 10 is less than 0. So this 0 is going to be 1 minus 1, exact same thing. And that's okay. I can consider 1 minus C1 squared. So, and then what I'm going to do, I bring this 10 this side, it's n plus 10, exact same thing. I need this one. And this is going to be C1 squared n. So if I put this one, this is going to be the result. So I have n plus 10 between C2 squared n less than C squared n or greater than C1 squared n. So, and then they got the square, they got the root. So this is going to be this one. I got it. So just it. And then I show this one. Just consider C1 equal to be 1 and C2 is equal to be a square root of 2. Does it make sense? Is this clear? So, but
Yeah, I think it's clear.
But another person, so maybe start what you can do as an example. Let's try this one. I'm going to post this one, yeah. Let's try with n not equal to 20. Do the exact same math, how I did it here. And then you will see, you will end up with different C1 and C2. It means that if I consider n not greater than 10, it means my C1 and C2 is going to be this one. If I consider n not equal to 20, I'm going to get to reach to the different C1 and C2. Still, I don't care about what you find for C1 and C2. As long as you can show that this is inequality is going to be whole, that's it. You proved it. But there are different ways. After I post this one, try this one with n not equal to 20 and see how you can reach to these numbers. Does it make sense?
Yes.
Okay, sounds good. Okay, great. So that's one of the things you need to do. All the homework, so when I'm talking about, okay, what is C1, C2, you just need to show these things is possible. It means that I can find C1 and C2 equal to this equation. That's it. So let's get back to just now we try. Let's get back to another notation. Now I know about the like big O notation, theta notation. Let's go back to omega notation. What is omega? Big omega. We have a small notation of O and then omega too, but we have the big O notation. So let's go back. Does it clear up to now? Is it clear?
Oh yeah, it's clear.
Okay, let's go back and then, okay, I talk about different things. So let's go back. It's really interesting. If you go back to everything, you say, okay, I talk about like, first of all, I talk about if it's like a between, it'll be between two C1 G of n, C2 G of n, it's going to be like a sandwich between. And then I go to another one. I'm talking about like finding an upper bound for it. It is upper bound. Now I'm going to go to find the lower bound for it. So it means like we have another definition, big omega of n. We just find the lower bound. As you can see, C of Gn is going to be lower bound. So it's going to be, definition is going to be big omega notation. It's going to be all the functions such that there exists a positive number C1 and N naught, that from that N naught onwards, you're going to have this one. It means f of n is going to be upper, so it's going to see G of n is going to be lower bound for f of n. It means the set of all functions whose rate of growth is the same as or higher than of G of n. It means it's going to be higher. So that's the other thing. So it's going to, we call it asymptotic lower bound. Instead of the other one, big O is going to be upper bound and big omega is going to be lower bound. But this is something interesting to see. Again, if I have f of n to be big theta of G of n, it means it's going to be big omega too. As you can see, like a sandwich, upper bound, lower bound. If I have theta G of n, it means that I have big omega of n and I have big O notation of n, G of n too. It means that still the theta of G of n is a subset of the big omega of n. So because you can see, as I showed earlier, it's going to be between both of them. So it's going to consider both of them. But as I explained earlier, this way is one way. It means if it's a theta G of n, it's not going to be true for the other way. Does it make sense? Is it clear?
Yeah, it's good.
Okay. Let's go to like, I want to show this one, exact same thing. If I want to prove it, what I'm going to do, I found out the C and N naught, so how it's going to work. So let's see, for example, I say, okay, a square root of this N is going to be big omega of log of n. You need to find C and N naught. So you just need to prove this one. It shows that it's going to be lower bounded by this. So probably you need to go do this like example, find C1 and N naught and show it's going to be possible. As I explained earlier, like for example, the other one. Let's go and find a relationship. As you can see, big theta of G of n from N naught onwards, so f of n is going to be like between C1 G of n, C2. If I talk a big O notation, it means after a while, everything is going to be like higher. As you can see this one, it's going to be from this part onwards. So it means that it's going to be upper bound of this function. And if I just big omega, like omega notation is going to be lower bound for this whole f of n function. Does it make sense? This is the relationship between big theta, big omega and big O notation. Is this clear?
Yeah, that
Probably-
makes sense.
Yeah, probably is one of the really important plot that you need to have in your mind.
So the theta is like a combination.
Yes, a combination. Yes, exactly. So this is a definition. There is a relationship, there is a theorem, say for any two function, g of n and f of n. F of n is going to be big theta of g of n if and only if f of n is big O of g of n and f of n is omega, big omega of g of n, as you explained earlier. It's going to be in the middle. It means if I want to show this theta, if I show these two, it's done. It means this is going to be this theta g of n is going to be like the subset of like going to be intersection between these two, as you can see here. If I go back to example, as you can see here, if I just consider like being like intersection of these two, I'm gonna get this one. So there are probably one of the things. In practice, we say asymptotic tight bounds are obtained from asymptotic upper and lower bounds. So this is gonna be the tight between, which is gonna be theta. It means it's gonna be between the obtained from the lower and upper bound, as you can see in this example. So it's tight between the lower and upper bound. Does it make sense?
Yep.
Okay, sounds good. Okay. Okay, why it's become really important? All of these things talking about big O notation, theta O notation. So this is coming from something. If I run an algorithm, so if I say, okay, I wrote a code, this is gonna solve the, like, for example, sorting problem for me. I don't care about best case scenario. Okay, some of the things that I give you a like list of numbers, and all of them is already in the sorting order. Only maybe two numbers at the end is not sorted. That is going to be best case scenario. It means it's already sorted. Only two of them is not sorted. That's we say base case scenario. But when we talk about algorithm, we care about worst case scenario. It means that none of the numbers in that list is in the order. Everything is not in the order. You need to change one by one to make sure this list is going to be ordered. So the runtime that we care about is going to be, the name is worst case scenario. It means that for example, for doing the sorting, I need to do all of them one by one. Let's write the example here. Okay, so probably it's not gonna work here. So let's see. Okay, can you see it here? So let's see. I have 1, 2, 5, 6, 5, 8. Okay, I want to sort these numbers. How can I sort it? What is the number of the execution I need to do? What should I do? Anybody? Yes, we just swap the 6 and 5. That's it. I don't need to do any other things. What I'm gonna do, I just change the numbers. Like I want to just change the swap between 5 and 6. It's gonna be 5, 6, and 8. So this is the best case scenario. I just need to change 2 of them. But let's see. If I have these, so look at this one. What should I do? If I want to do these things, if I want to just sort this. Let's think that I need to swap. So first of all, I need to swap between 12 and 31. And then when I do this one, it's like a 12, 24. So I need to swap 24 for 23. Let's do it, for example, one by one. If I want to do this, I say, okay, let's swap that. So going 12, 24, 31, 31, and then 23. So I see, okay, it's not only sorted. Let's do another step. So I'm gonna say 12 and then swap between 23 and 24. It's gonna be 31, 31, and 24. Still is not gonna be sorted. Let's do another. So it's got 12, 23, and 24, 24, and 31, and 31. You can see I have only 5 numbers. I need to do 4 different swipes to just get to the sorted order. This is going to be the worst case scenario. It's going to be worse. It was going to be worse if this one was 32. If this number was 32, it means that I need to swap everything one by one. This is going to be worst case scenario. It means none of them is sorted. I need to do one by one. But in the algorithm, when we are talking about theory, we don't care about this option that is going to be best case scenario. We're caring about worst case scenario. Does it make sense?
Yeah, makes sense.
Okay. So when I'm talking about worst case scenario in algorithm, runtime is going to be big O of f of n. Why? Because it's going to be upper bound. Upper bound is not, it means that it's not going to get worse of that. That's going to be the best thing. That's going to be the worst things you are going to get. If you go back to look at the plot, let's go back to plot. So here, look at this one. If I'm talking a big O notation, it means it's not going to get worse than C of G of N. It's going to be the worst thing's going to happen is going to be that. So it's going to be the worst case scenario is going to be this one. So what you're going to say is, okay, O notation of f of f is going to bound on the worst case runtime. It's going to be the worst case. It bounds on the runtime of every input is going to be the worst one. So other than that, it's not going to be anything. But theta of f of n bound on the worst case runtime, it doesn't mean that it's going to be bound on runtime of every input, because it's not going to be worst case, because it's going to be in the middle of this thing. Runtime of big omega of n is going to be best case scenario. Why? Let's go back. Look at this plot. So here, if I have a big omega notation, you can see the best thing I can get in the best scenario is going to be C of G of n, because it's not going to get better than that, because it's lower. The lowest I can get is going to be C of G. So this is going to be the best case scenario, and this is going to be the worst case scenario. Does it make sense? It means if you give me the algorithm, I can say, oh, your algorithm at the best scenario is going to be this one. It's going to do, for example, I say, okay, in the best scenario, it gets 20 seconds. And because they worse, it's going to get in worst case scenario, it's get 100 seconds. That's the important things. At the end of the day, I don't care about like that much about the best scenario. So like, okay, in worst case, okay, if you have millions of like document, at the end of it, it's going to get 20 seconds. That's it. That's the most important things you need to know. Does it make sense?
That makes sense.
Okay. So this is some of the reason I explained this one in really detail. All the other part of the class is going to be based on this big O notation, because any algorithm we write, we care about, okay, what is the runtime? What is the big O notation of that? If this algorithm is good enough or not? What is the worst case scenario? What is the best case scenario? That's the only things that go through all of this one by one, because all the other parts of the class is really dependent on this one. Okay, so let's see. Okay, like for example, there are so many sorts. I'm gonna teach this one in the class too. We have an insertion sort. It is gonna be the big theta of n squared in the worst case scenario. Why? Because as I explained everything in the past, if I have a big theta notation, it means I have a big O notation too. And if I have the big O notation, it means that I know the worst case scenario. Does it make sense? So I can say this algorithm in worst case scenario, it's going to take big O notation of n squared. It's not going to get worse than that. Is it clear?
Yeah.
Okay, so that's one of the things. So you care about worst case scenario. So now I have an algorithm. I wrote an insertion sorting algorithm. And I said, okay, in worst case scenario, it doesn't matter how many, like a number you are gonna sort. It's gonna be big O of n squared. It's not gonna get worse than that. So that's one of the things. So any sorting algorithm must look at each item. So sorting is going to be like big set of n. So I'm going to talk about this one in the next session too. So we are talking about different, for example, merge sort is going to be big set of n log n in worst case scenario. As you can see, n, as I explained, n log n is better than n squared. It means this is going to be faster than insertion sort. For example, if I want to check between which sort I'm gonna use. I got a worst case scenario, merge sort takes this time and then insertion takes this time. So I'm gonna go with merge sort. It means that in the worst case scenario, merge sort is gonna be better than insertion sorts. So that's some of the things, for example, if you see in the homework or the like a midterm that writes a best sorting algorithm, you need to write the one that takes less time than the others. So it's gonna be probably faster. Is it clear?
That's clear.
Okay, so I think we are good up to now. I have two parts of the presentation. So this one and the other one, when I started from at the beginning of class, I will post both of them in the Canvas so you can look at it. Just there is the problem that I showed in the class. Just be ready for that one, like maybe quiz us on Friday tomorrow. Like be really specific. Is this one gonna be like as I showed you guys, it's going to be big theta or that one or not, like the n squared one. So how about 2 or power of 2n? Is this going to be subset of the theta of 2 power of n? 2 power of n, yeah, you need to show that one. That's the first part. And then other than that, so we keep going through all the other notations, solve other problem together tomorrow. And we are going to have one more quiz on like Thursday. The tomorrow one is going to be really easy. It's going to be yes, no. So you say, how about this one? Is it yes, no? And just you say like a little, really simple explanation. Just gonna heads up for tomorrow. Does it make sense?
Yeah.
So quiz tomorrow, just yes or no.
Yeah, a
on-
little explanation why you think is correct or not. For example, I found C1, C2 be these numbers. So you have time to think about it up to tomorrow, because there is explanation about, oh, why you consider C1 and C2. Yes or no, and what is C1 and C2. That's it. So I could not, there is no C1 or C2, or if there is C1 and C2, what is C1 and C2?
Do the C1 and C2 have to be like the lowest possible C1 and also the highest possible C1 and the lowest possible C2?
Not exactly. If you could show, because the purpose is proof. So if you could find n naught and C1 and C2, it doesn't matter if
I
it's
see.
lower or not. As I showed you in the PDF, you can find n naught to be 10, and you find C1 and C2 different when you consider n naught to be 20. So it doesn't matter, you want to go with 10 or 20. You just need to show that inequality is going to be whole. Yeah,
That makes sense.
the quiz is going to be graded, yeah. Like it's just show the involvement in the class or interaction. So if you look at some of the parts, because you need to keep focusing and just keep going on learning about this thing, because it gets more and more every session, and then you need it. Because if you don't learn about like big O notation, like maybe next week, if I write a code and say, okay, what is the big O notation of this pseudo code? You don't know. Or in another homework, it's okay, write a code that the pseudo, like the big O notation is going to be linear. So you don't know what is the big O notation. So make sure that you just go through that one, look at what I explained already, see what is how the problem going to be solved. And then you will get back tomorrow and I will explain after the quiz, I will explain it myself. Does it make sense?
I have a question.
Sure.
Are we gonna have a homework due this Friday?
Probably not.
Okay.
No. Probably the thing's gonna happen. I will submit homework like this Thursday, this Thursday, and then you have 1 week until next Friday. The week after that to submit the homework, because I give one period of 7 days to finish the homework. Does it make sense?
Yes.
Okay, I will submit a quiz on Thursday, and then you have 1 week until next Friday to just submit it. And then if you have any questions, so you can ask after one of the session that we have. So probably it's gonna be fine.
Is the quiz graded on correctness or just participation?
I like correctness is better because you will learn. Yeah, at the end of the day, I will look at how you explain what's going on. So yeah, it's not that there is I want you guys to try it and understand how it works, or how you're gonna prove it.
And how do we submit the quiz? Do we need some special software or something like that?
No, it's gonna be in Canvas. So just open a quiz there, and I just give you access to just type your code or just upload your note there. So I'm gonna do it tomorrow. Yeah, you can write. I can give you access to uploading the notes, or just Word document or anything. You can upload it, anything you want. You can upload your handwriting note.
Okay, thank you.
You're welcome. So I think our class gonna be done right now. So if you have any question, I would be happy to answer. If not, so have a great evening and talk to you guys tomorrow.